Today we want to continue the study of planets that move around the Sun. Okay, these objects are planets that are under the influence of central forces, and we saw that the motion of a planet it will depend on the form of the potential energy that that planet has. Okay, we saw that for a planet, we know a potential energy V that is equal to negative k over r, which it can be defined from the Newton's gravitational law. Okay, so on previous videos we have been watching that we are able to find two equations to describe the motion of the planet around the Sun. Okay, one is to find the orbit of the planet. Okay, we have seen this equation on a previous video, and we got to this result here. We see here that we have the polar version of the ellipse equation. We see here that we have the polar variables r and theta. Okay, so we relate r and theta to get a polar equation that is actually an ellipse. And remember, if we have an ellipse, the eccentricity is less than 1, and that means that the total energy of the planet is less than 0. Okay, so what we want to do in this video is now to consider the second equation that we found. Okay, we already demonstrate how to get to this equation, but look that the difference here is that we are involving time and the distance r that separates the Sun from the Earth. Okay, in that case, for example, let's say that the Earth is here. That distance r is going to be the distance from the Sun to the Earth. Okay, so look that r depends on time. Okay, for example, if the Earth is here, we will have a different value of r. So we want to find in this video a function that relates r with t, which is the time. Okay, so what we need to do first is to look to this equation, and we see here that it depends on the potential energy of the planet. So but we know what is the potential energy is this expression over here. So we are going to take this equation and take it into the integral, and let's see what happens if we do that. We are going to get the next. We are going to get, this first integral, we can just see it as the next, plus or minus t0, where t0 is the initial time, and this is going to be equal to the integral of dr over the square root of 2 over m times e negative v, but that will be plus k over r, looking that the potential is, it has a minus. So this is going to be minus L squared over 2mr squared. Okay. So what we are going to do now is to multiply everything by 2 and then take a common factor 1 over mr squared. Okay, so this is going to be dr all over the square root of 1 over m squared r squared times, this is going to be e times mr squared plus k, 2 times actually, 2 times k mr minus L squared. Okay, and we see here that we can cancel this square root with these squares. Okay, because they are positive quantities, so this is going to be the integral of dr all over, we are going to take m and r here. This is mr dr, so down here we are going to get the square root of 2e mr squared plus 2k mr minus L squared. Okay, So what we are going to do now is to examine this expression here. 2emr squared plus 2kmr minus l squared. We are going to prove that, well, this expression can be written as the next. 2me times r plus k over 2e squared minus mk squared over 2e times 1 plus 2el squared over mk squared. Okay? So look, if we take this expression, well, we can see that this is going to be equal to 2me times r squared plus rk over e plus k squared over 4e squared minus mk squared over 2e minus, well, it will be just l squared here. Okay, so this is 2mer squared plus 2mrk, and then plus mk squared over 2e, and then minus mk squared over 2e minus l squared. Look that these terms will cancel, and we are going to get what we started with. So yeah, that means that we can write this as all this. So you might be wondering why, because it seems a little bit more complicated, but you are about to see that it will help a lot. So we are going to get that plus minus t minus t0 is equal to the integral of mr dr all over the square root of 2me times r plus k over 2e squared minus mk squared over 2e times 1 plus 2el squared over mk squared. Okay? And well, on a previous video we were watching that we can define the eccentricity of the ellipse as the next. E squared is going to be equal to 1 plus 2el squared over mk squared. Okay? And other thing is that we saw at the beginning of the video that a is equal to negative k over 2e. So that means that e is equal to negative k over 2a. Okay. So look, that is what we have here, and that is what we have here, the eccentricity. So if we rewrite this expression, we are going to get plus minus t0 equals the integral of mr dr all over, well, the square root of 2me, but e is this, so negative k over 2a, then times, well, let me just write e just to make it easy. We'll change it later, and this is going to be r, then minus a squared minus mk squared over 2e, and then the eccentricity squared. Okay. Okay, so we are going to take a common factor 2me of this expression. This is going to be the integral of mr dr times, over the square root of 2me times r minus a squared minus, well, k squared over 4e squared e squared. Okay. But look, well, we have seen that a is equal to negative k over 2e. So if we raise this to the second power, we are going to get plus k squared over 4e squared, which is actually the same thing that we have here. So this is a squared. Okay? So this is equal to the integral of mr dr over the square root of 2me times r minus a squared minus a squared e squared. Okay? So what we are going to do now is to change e for its definition in terms of a. We saw that e is equal to negative k over 2a. So this is going to be equal to the integral of mr dr all over, well, 2m times the square root first, 2m times negative k over 2a. And here we are going to switch this just to cancel this minus. Okay, so this is going to be, well, a squared e squared minus r minus a squared, and that will change that to a plus here. Okay, we can cancel these twos, and this is going to be equal to the integral of mr dr all over the square root of mk times a squared minus r minus a squared. And here is an a, okay? So looking at m, k, and a are constants, we can take them out from the integral, and it's easy to see that we are going to get the square root of a times m over k times the integral of r dr all over a squared e squared minus r minus a squared. Okay, well, we can erase this parenthesis actually, and we actually get an integral that, well, it is well, it seems to be solvable by the trigonometric substitution method. Okay, so let's do it the old way. We are going to draw a triangle with a new variable, let's say theta. Okay, well, let's say phi, and let's say that, well, the hypotenuse is going to be equal to EA, then this side is going to be equal to e squared a squared minus r minus a squared, and this is going to be equal to r minus a. Look that, well, the Pythagorean theorem is here. So we are going to say that cosine of phi is equal to adjacent, which is r minus a, over hypotenuse, which is EA, and this is, well, that r minus a is equal to EA cosine phi. Okay, another thing that we see is that, well, the sine of phi is equal to all this expression, the square root of e squared a squared minus r minus a squared over the hypotenuse. So we are going to write this here. And from here, well, we can take the derivative of r with respect to phi to see that this is just going to be negative EA sine of phi. Okay, so what happens if we substitute on our integral? Well, we are going to get that plus minus t0 is equal to the square root of am over k times the integral of r, but r, well, is going to be equal to, well, a plus EA cosine of phi from here, but that is actually a times 1 plus e cosine of phi times dr, but dr is, well, a negative EA sine of phi d phi all over, well, all this expression that we have here, that we saw that it is equal to this. So we can say that here at the denominator we are going to write EA sine of phi. So we easily notice that this cancels with this, this with this, this with this, and we get, so this is equal to, Well, this can be seen as the square root of a squared. So this is equal to the square root of a cubed m over k times the integral of 1 plus e cosine of phi d phi. And if we, well, negative actually, and if we integrate, we are going to get the square root of a squared m over k times negative phi negative e, well, the integral of cosine is the sine, so sine phi. Okay, so looking at, well, we had that this is equal to plus minus t0, we can just see this as negative minus t0 equals the square root of a squared m over k times phi plus e sine phi. Okay, in this case we need to notice that, well, it's going to be very hard to solve this equation for phi, but what we can do is that establish that, well, if we let the Earth makes a whole turn around the Sun, well, it will be equivalent to say that phi well, takes the value of 2 pi, okay, because it is a whole turn around the Sun, okay, and that motion is going to be completed on a time which is the period of the motion, and we are going to name that period t. Okay, so it's like some kind of initial conditions of the motion, okay, to establish some useful result, looking that we are not able to solve this equation for phi. So if we take this result, we see that for the time we can just take the period and substitute 2 pi in phi. Okay, so we are going to get that t, the period, is going to be equal to the square root of a cubed m over k times 2 pi plus e sine of 2 pi. But sine of 2 pi is 0. Okay, so this is just going to be equal to 2 pi. Okay, so what happens if we raise this to the second power of the whole equation? Well, we get that t squared is equal to a cubed times m over k times 4 pi squared. So if we order this, we are going to get 4m pi squared over k times a cubed. So look, this is actually already the Kepler's third law. Okay, this is the third law of Kepler. And look, it says that, well, the square of the time that takes the Earth to give a turn around the Sun is equal to a constant times the major semi-axis of the ellipse of the Earth raised to the third power. Okay, that is what the third law of Kepler says. And, well, we have shown this in a mathematical way. So that is the equation that proves the third law of Kepler. So feel free to leave a comment or a question to answer it. And yeah, well, this will be just the final result of the video.